Alrighty, we are on to, oh my goodness, I did give you guys another slide. Oh well, we didn't need it. It's funny. Okay, so electric field lines. So I kind of wish this stuff would have been before the last two examples, just because this shows you the direction, and so you guys kind of already know this a little bit now. So it's just saying that it's difficult to make a visual representation of an electric field using vector arrows. So it's saying that another visual representation is a sketch of electric field lines. And these are representing both the magnitude and direction, so the vector. You can see here on the interpretation of electric field lines that wherever the point is, the direction of that electric field is tangent to that point. Okay, so same direction as the arrow. This illustration is showing you that the closer those electric field lines are, the stronger that electric field is, and the weaker they are when they're farther apart. Just kind of think of like if these were two magnets that were attracted to each other. That's going to be pretty strong field. Whereas, if these are the magnets, then that's going to make it a lot, weaker. All right, so rules for sketching the electric field lines. This is the one that I wish it kind of would have shown you before, because this is showing you that you've got a positive charge, you've got a negative charge, and you can see that the field lines are coming away from the positive and they're going to the negative. And see how this one over here, this +3, is a little bit bigger of a charge than this -2. So it's got, some more field lines coming out of it than the -2 gets. And you can also see that these lines are never intersecting. It's impossible for them to do that. So whenever you're drawing it, it has to be where they do not intersect. Okay? And it is also saying here that the negative charge is proportional to the magnitude of the charge. So the total number of lines that you draw, the more lines, the better representation of the field. All right, so yeah, this is just saying that it's impossible for those electric field lines to cross like that. This is showing you a single point charge, and you've got a negative, a positive. They're the exact same as far as number wise, so they have the exact same number of arrows or vectors coming off or towards them. And then it's also showing, this one's kind of a little bit harder to see, I think. Maybe it does a little bit better one. Not really. So this is showing that the lines are close together, and you can see kind of this one. They're all supposed to be the same size. It just looks different to me. Okay, so where are we? Here we are. So a pair of point charges with equal and opposite charges, that's called a dipole. My goodness. So that's literally two poles. Similar to the Earth, we've got the North and South Pole, and they make lines just like this that we can't see, and it's just, like our magnetic field between them. So it's kind of cool to think about. You've got, here's a pretty cool picture. This is showing you that at a point, depending on where you are on the electric field, you could have these X and Y values, or these negative and positive values, okay, depending on what point you are. So we've got another example, 16.8. So a thin metallic sphere shell of a radius carries a total charge, which is positive, and the charge is spread out evenly over the shell's outside surface. It says to sketch the electric field lines in two different views of this situation. So, part A. All right, the spherical shell is tiny, and you are looking at it from distant points. So, here you've just got this shell that's positive, it says. So, it wants you to basically just draw, these field lines here. And then it says to distinguish, I think, if you're looking at it closer or farther away from the shell. So let's say this one's kind of farther. So the farther that you get away from it, the less it's going to have, the lower electric field it's going to have. But the closer you get to it, it's going to be a little bit bigger, right? These are right on it. So they've got the biggest magnitude there. Wow, I gave you a whole nother slide for that. Okay, so for part B, it says you're looking at the field inside the shell's cavity. So it said that the shell was positive. So let's say we have a case where the shell's positive, but inside this shell, it's negative. So that would show that like you would have these electric fields that were kind of pointing out like this. But inside, you could even have electric fields that were like this, okay, creating it to be like at an equilibrium. Okay, all right, so now we've got the motion. Gosh, I wish you guys could see that. There we go. Motion of a point charge in a uniform electric field. The simplest example of how a charged object responds to an electric field. Like, so if you put something inside this right in here, okay? Now, the way that I always explain it kind of is just think about it almost like you were going to take a rock and pull it away from the earth. So the higher you pull it up. And so this is the rock. If I let go of that rock, what's going to happen to it? I'm thinking like gravitational right now. It's going to fall, right? So if I let go of this charge right here, it's going to have some potential to go like that direction, correct? Because those electric field lines are going to go to the negative charge. So this is just showing you that if you do that, you could have a situation where you end up with some acceleration, which we showed a little bit ago, didn't we? Whenever we were solving for acceleration of that electron. Okay. So I think we have one like that actually coming up. So this is saying the acceleration of a charged particle due to an electric field. I swear, they did it like backwards on this PowerPoint. So weird. Okay, so you've got a cathode ray tube, which is sort of like the first thing that they created, that they made a long time ago, that sort of proved that there were these things called electrons. And it's used to accelerate electrons. You can, in televisions, computers, different things. And so the electrons are passing through a hole in a cathode, and they are then accelerated by an electric field between the cathode and the anode. So this is how, electricity is working, right? So you create this field, and then these electrons are zipping through, causing there to be electricity, basically, to go through these wires and all kinds of different situations. This one's, talking about a cathode ray. So suppose an electron passes through the hole in the cathode at a velocity of 1 × 10⁵ meters per second. The electric field is uniform and has a magnitude of 1 × 10⁴. So it wants to know first, what's the acceleration of the electron? So, you can have all of that. Or let's write some stuff of our own. Well, it already wrote. Let's see. It's giving you the initial velocity, which is 1 × 10⁵. It's telling you that the separation between the plates is 0.02 meters. And it gives you that the electric field is 1 × 10⁴. And you will need to know the mass of an electron, which is essentially 9.11 1 times 10 to the negative 31st. And the charge of an electron is this negative 1.6 times 10 to the negative 19th. So first we're finding the acceleration, and then we're finding the velocity. Okay, so for acceleration first. So first, if we do the electric force, so we've got the electron or the charge times the electric field, okay? If we take our electric charge here, which is this 1.6 times 10 to the negative 19 coulombs, times our electric field that it gave us, which is 1 times 10 to the 4th Newton per coulomb, we end up with an electric force of 1.6 times 10 to the negative 15 newtons. Okay? Now, as far as acceleration is concerned, acceleration is force divided by mass. Well, we just found the force. So we've got 1.6 times 10 to the negative 15 newtons divided by the mass of an electron, which gives you an acceleration of 1.76 times 10 to the 15th meter per second squared. All right. Now, and it's wanting us to find that final velocity after. Okay? So we needed to have found the acceleration first. This is going back to some kinematics equations. So kind of a blast from the past here. I'll just kind of give you a little bit of a review of those for a minute. So you've got, gosh, I hate when it does that. You've got this one. Remember that one? That's kind of the long one. You've got this one. You had this, where it was like the initial velocity plus the final velocity divided by 2. You have your basic ones, which, like, you could find the average velocity if you knew the final and initial position and time. And then you could also do the same thing for that one. But are we given time in this scenario? No. So that eliminates this one, this one, this one. Do we know the final velocity? No. So that eliminates this one. So it leaves us with that second one right there. So if we solve just for final velocity, then we got to do the square root of velocity, the initial velocity squared, plus 2 times the acceleration change of x. Does it give us all that other information? It sure does. So that initial velocity that it gave was 1.0 times 10 to the 5th squared plus 2 times 1.76 times the change of x. So it doesn't give us an initial, so we're just going to have that it's 0.02 meters. Okay, and you got to do the square root of all of that. And you should get 8.4 times 10 to the 6th. Yeah. So there you go. You've got your acceleration and you've got your final velocity. All right, I'm going to end